This is Srikanth as Assistant Professor of EEE Department. In this session, I am going to cover the full wave rectifier with diodes. A full wave rectifier, the name itself says it converts both half cycles into a DC supply or whatever the constant voltage. Either it may be positive voltage or it may be negative voltage. A full wave rectifier converts both halves of each cycle of an alternating wave into pulsating DC signal. We are going to get the pulsating DC signal that is going to have only a positive values or negative values. The input AC waveform and the circuit diagram and final output voltage waveform are shown in figure. So here, for full wave rectifier, in order to give the supply to the two diodes, we are using a center tapped transformer. Center tapped transformer that is going to have here, this is the neutral, this is the phase P1. Let us consider phase 1. This is P2. P1, P2. And this is the phase and this is the neutral. This is the phase and this is the neutral. Neutral is common to both the diodes or both the phases. So here these diodes are connected in series with the transformer first phase and second phase. And for the first phase, it is connected to the anode of the diode is connected to P1, and in the same way, anode of the diode D2 is connected to P2, and which is connected to this resistive load. So here, when we are giving, this is the AC input, this is the AC input. When we are giving AC input during the positive half cycle, this will be positive and this will be negative. And here, when this is positive and this is negative, the diode anode is connected to positive, so the diode D1 will become forward bias. Once the diode D1 is forward bias, so the supply will flow through P1, diode, load resistance and neutral. So here, this is the supply flows and load voltage is equals to, if we take, this is our positive terminal of output voltage, this is the negative terminal of output voltage. This positive terminal is connected to the positive of input voltage, So here, when this is positive, output voltage positive is connected to positive of input voltage, the output voltage is equals to the input voltage, that is Vm sin omega t. And now here, when this is positive and this is negative, and then this will be positive and this will be negative. This terminal will be positive and this terminal will be negative. So anode is connected to the diode negative is connected to the D2 anode. So when the negative is connected to the anode of the diode D2 is a reverse bias. So this diode D2 will not conduct. This D2 will not conduct during the period 0 to pi. After pi, these terminals are going to get changed. This will become negative and this will become positive. And here, this will become positive and this will become negative. So when this becomes the negative, immediately D1 gets a reverse bias, and when this terminal becomes the positive, D2 gets forward bias. Once D2 gets forward bias, the positive is connected to the positive of output voltage. So again the output voltage is equals to minus of input voltage. So in this cycle we are having minus Vm sin omega t. So minus of minus will become plus. We are having during the period pi to 2 pi, we are having the negative of cycle. So minus of input voltage will become the positive. Here we can write the equation like this. V naught of t is equals to Vm sin omega t, where 0 is less than or equals to t is less than or equals to t by 2, which is equals to Vm sin omega t minus pi, which is t by 2 is less than or equals to t is less than or equals to t. Now let us go with the average value of output voltage. Here, for calculating the average value of output voltage, we have to go with the calculation of the average output voltage by using the time period. That is, here our waveform is of symmetrical, which is unsymmetrical waveform, only which is having only the positive half cycles. Here the cycle is repeating after pi. After pi time period, the cycle is repeating. So here 1 by t integration 0 to t v naught of t dt. Here 1 by t by 2 integration 0 to t by 2 Vm sin omega t, if we substitute the limits. So here 2 Vm by pi 2 Vm by t into integration 0 to t by 2 into sine omega t. Integration of sine is cos omega t. So here when we take cos omega t, minus cos omega t, which is equals to 2 Vm by pi into integration, the limits minus cos omega t by omega into dt, which is equals to 2 Vm by t. Here, if we substitute 2 Vm by t into minus cos omega t, where the limits are from 0 to t by 2. So here if we take t value as omega, we are going to get omega t value as pi. If we take, we are going to get the value as here 0 minus of minus 1, which will be equals to 2 Vm by pi. So we are going to get the output voltage, average output voltage as 2 Vm by pi. And next, if we substitute for calculating the RMS value of output voltage, 1 by t integration 0 to t v naught square of t dt whole power 1 by 2. Here if we substitute the limits Vm square by t by 2 into integration 0 to t by 2 sine square omega t dt whole power 1 by 2. Here in place of sine square omega t, if we substitute 2 sine square omega t, if we substitute 1 minus cos 2 omega t, and if you do the integration and substitute the limits, we are going to get the VRMS value as Vm by root 2. Now we got V average and VRMS value. Once if we know the V average and VRMS values, we can get the ripple factor, where the ripple factor is equals to square root of VRMS by VDC whole square minus 1, which is equals to square root of pi by 2 root 2 whole square minus 1, which is approximately equals to 0.48. 0.48. Now, let us go with the calculation of efficiency. Here, efficiency is equals to DC output power by AC output input power, that is equals to VDC square by VRMS, VDC by VRMS whole square into 1 plus RF by RL. If we substitute VDC and VRMS value, VDC value as 2Vm by pi, VRMS value as Vm by root 2, we are going to get this value as 0.8106 into 1 plus RF by RL. In reality, RF value is smaller than RL. If we neglect the RF compared to load resistance, then the efficiency of the rectifier is maximum. Therefore, efficiency of maximum efficiency is 81.06% for full wave rectifier, whereas for half wave rectifier we got around 40. And the next one is the form factor. Form factor is nothing but it is the ratio of RMS voltage to the average voltage, that is equals to pi by 2 root 2, which is equals to 1.11. And here peak inverse voltage of full wave rectifier, here peak inverse voltage or peak reverse voltage can be defined as the maximum value of a diode which occurs at the peak of the input cycle when the diode is in a reverse bias condition. Here for peak inverse voltage of center tapped full wave rectifier is 2 Vm and of the bridge rectifier is Vm. If it is a center tapped rectifier, 2 Vm is the maximum voltage, negative voltage which can appear across the diodes. Whereas if it is a bridge rectifier, the maximum voltage which is appearing across the diode is Vm. And the next one is peak factor. Peak factor of full wave rectifier is, peak factor is equals to the peak value by RMS value, which is equals to root 2. Vm by root 2, which is equals to root 2. The applications of full wave rectifier. Full wave rectifier is of two types, center tapped and bridge rectifier. Both these rectifiers are used for following purposes, depends upon the requirement. The following of the full wave rectifier applications. It can be used to detect amplitude of modulated radio signal, and it can be used to supply polarized voltage in welding. And the bridge rectifiers are widely used in power supply for various applications, various appliances, as they are capable of converting the high AC voltage into low DC voltage. The advantages of full wave rectifier. Full wave rectifiers have higher rectifying efficiency than half wave rectifier, and this means that they convert AC to DC more efficiently. because they have low power loss because no voltage signal is wasted in the rectification process. Here, during the rectification process, no voltage signal is wasting. So, there is no less power loss in this particular full wave rectifier. And the output voltage of center tapped full wave rectifier has lower ripples than half wave rectifiers. And the major disadvantage is center tapped rectifier is more expensive than half wave rectifier and tends to occupy lot of space because we need a transformer. Transformer cost will be more as compared with the electronic devices. So this center tap transformer, which is going to have more expensive than the half wave rectifier which we have studied. And this is the comparison of different parameters related to the half wave and full wave rectifiers which are given below. So here the parameters half wave rectifier and full wave rectifier. First, when we consider the number of diodes in the half wave rectifier, the number of diodes is only 1. In full wave rectifier, either 2 is for center tap transformer, 4 is for bridge rectifier. And maximum efficiency is 40.53%, whereas for full wave rectifier, 81.06%. Here the peak inverse voltage will be Vm for the half wave rectifier and Vm or 2Vm, that is Vm is for bridge rectifier and 2Vm is for center tap rectifier in case of full wave rectifier. And average voltage on no load is Vm by pi. Average voltage on no load is 2 Vm by pi for full wave rectifier. And VRMS on no load is Vm by 2. And VRMS on no load for full wave rectifier is Vm by root 2. And the ripple factor is 1.21. And for a full wave rectifier, the ripple factor is 0.48. The form factor is 1.57 for half wave rectifier. For full wave rectifier, it is 1.11. The output frequency for half wave rectifier is F. For full wave rectifier is 2 times F because we are going to get 2 cycles in one complete cycle. So the frequency is double. Now let us see the operation of diode bridge rectifier. So here when we consider this is phase and neutral, and this will be the voltage which is going to appear across the phase, and across the neutral the voltage which is going to appear is in this way. So here when during the period 0 to pi, 0 is less than or equals to, t is less than or equals to pi. During the period 0 to pi, the diode D1 anode is connected to phase of input voltage, and phase of input voltage is positive, and hence D1 gets forward bias. And whereas D4 is connected to, D4 cathode is connected to positive of input voltage, that is phase of input voltage, so D4 gets a reverse bias. And here again D2 is connected to neutral, so D2 is connected to neutral. Here the neutral voltage is of negative voltage, so cathode of D2 is connected to the negative voltage. So when cathode is connected to the negative voltage, then the D2 will be in forward bias. And in the same way here anode is connected to the negative of input voltage, so D3 will not conduct, D3 will act as reverse bias. Hence during the period 0 to pi, D1, D2 are going to conduct. When D1, D2 are going to conduct, the supply will be flows through phase D1, load, and D2 and neutral. Here the output voltage, this terminal if we take positive, this terminal if we take negative. Output voltage positive is connected to phase of input voltage. So the output voltage will be equals to input voltage. But this is the input voltage. If we take whatever the input voltage we are giving, the same as we are going to get the output voltage. Here the blue line indicates the input voltage and red line indicates the output voltage. And this is during the period 0 to pi. And if pi is less than or equals to t is less than or equals to 2 pi. In this case, this is during the period pi to 2 pi. Here the negative of input is connected to D4 cathode. So D4 will be forward bias. And D3 anode is connected to positive of neutral. So D3 will be forward bias and D1, D2 will get reverse bias. Immediately, once if they get the negative voltage, immediately they are going to get turned off or reverse bias condition. So once the D1 and D2 are reverse bias, and here D3 and D4 are going to conduct. D3 and D4 are going to conduct. Once the D3 and D4 are going to conduct, once the D3 and D4 conducts, here the positive of output voltage is connected to the phase of input. The positive of output voltage is connected to neutral of the input voltage. So we can write it as the output voltage is equals to minus of input voltage. So here the output voltage is minus of input voltage. So negative of negative will become positive. Here we are having negative of cycle. Minus of input voltage is nothing but which will be opposite to the input voltage. So which is we are going to get minus of minus will become plus positive output voltage. Like this we are going to get, and if this cycle will continue, and this is during the conduction of D1, D2, and this is during the conduction of D3, D4. Again D1, D2 and D3, D4. Like this we are going to get the conduction in 2 cycles. This is diode bridge rectifier, and here only the change is the forward resistance of the diode is going to be dropped in this. So only whatever the output voltage will be equals to input voltage minus 2 times the whatever the forward voltage drop across the diodes. Now let us go with the half wave rectifier with capacitor filter. Filter components are used to convert or smoothen the pulsating DC waveforms into constant DC waveforms. They achieve this by suppressing the DC ripples in the waveform. Although half wave rectifiers without filters are theoretically possible, they cannot be used for any practical applications. Generally, only theoretically we can study with the rectifier output directly, whereas when we go with the practical cases, definitely we have to add the filters in order to get the constant DC, because we don't want the pulsating DC for our regular applications. So the DC equipment requires a constant waveform. We need to smooth out this pulsating waveform in our day-to-day component requirement. And this is why in reality we use half-wave rectifier with a filter. A capacitor or an inductor can be used as a filter, but half-wave rectifier with capacitor filter is most commonly used. Generally, we are going to use the half-wave rectifier with capacitive filter. And the circuit diagram below shows how a capacitive filter can be used to smoothen out the pulsating DC waveform into a constant DC waveform. Here is the connection. This is the capacitor filter which is connected in parallel to the load. So when the diode conducts during the period positive half cycle, that is during the period 0 to 90 degrees only. Here not 0 to 180 degrees. Here 0 to 90 degrees, the conduction takes place with the diode forward bias condition. So during this period, once the diode is conducting, the current flows through the diode and capacitor. Here the capacitor is going to charge the voltage. Capacitor is going to charge the voltage. Once the capacitor is charged, after reaching the maximum value, even though the diode voltage, that is whatever the input voltage is reducing to 0, the output voltage is not becoming 0 because here across the load a capacitor is connected. So the capacitor voltage will appear across the output. Output voltage is equals to V capacitor voltage across the capacitor. And this capacitor voltage will discharge its voltage. And here we are assuming that there is a continuous conduction of the capacitor voltage in the negative half cycle. So here, after this point, the voltage is reaching to some reduced voltage, and this will be up to the next positive half cycle. Once if we reach the next positive half cycle, again capacitor will charging and discharging. In the positive half cycle, for 90 degrees period, the capacitor is going to charge, and remaining 270 degrees, the capacitor is going to discharge. And we are giving such that the capacitor has highest value which will store the energy which has to produce the complete voltage. So with this, the constancy in the output voltage will increase. You can see previously we are having, these are the pulses in the output waveform. Now here the pulse quantity is reduced. So after, if we go on using the next filtration, in that case we are going to get a constant DC. And the next one is with the center tapped full wave rectifier, we get a pulsating DC voltage with a lot of ripples as the output. When we take any full wave rectifier, we are going to get lot of ripples because in the positive half cycle we are going to get one cycle, and in the negative half cycle we are going to get one more positive half cycle. So in order to get the pure DC voltage, we have to go with the filter. Here we replace a capacitor across the load. The working of the capacitor filter circuit is to short the ripples and block the DC component. So it flows through another path and is available across the load. During the positive half cycle, the diode D1 starts conducting. The capacitor is uncharged. When we apply an input AC voltage, which happens to be more than the capacitor voltage, it charges the capacitor immediately to the maximum value of input voltage. At this point, the supply voltage is equals to the capacitor voltage. And when we go with the full wave rectifier with capacitor filter, the positive half cycles, once 0 to pi by 2, the capacitor is going to charge. Then after, capacitor will discharge and it will reach some other point in the next half cycle. It will reach some other point in the next half cycle. After reaching the some other point, again it will increase the voltage up to the next pi by 2, 180 plus 90, 270 degrees. After that, again this voltage will reduces and again increases, decreases. Like this process, charging and discharging process will take place, which will smoothen out more in the DC output voltage as compared with the half wave rectifier. Here the ripples are reduced in the full wave rectifier. When the applied AC voltage starts decreasing, the less than the capacitor starts discharging slowly. But this is slower when compared to the charging of the capacitor. Which is the charging of the capacitor will take very less time, but discharging will take more time. And it does not get enough time to discharge entirely. And the charging starts again because immediately we are getting the next cycle. So before discharging the capacitor to 0 itself, we are going to charge the capacitor again and again. So around half of the charge present in the capacitor gets discharged. During the negative half cycle, the diode D2 starts conducting and the above progress happens again. This will cause the current to flow through the same direction across the load. Now let us go with the full wave rectifier with practical diode. When we go with the practical diode full wave rectification, the positive half cycle when D2 of D1 conducts, the output voltage will be equals to V0 minus Vs plus V gamma is equals to 0. Here the V gamma is the voltage drop across the diode. That is nothing but forward voltage drop across the diode. So the output voltage is equals to input voltage or source voltage Vs minus V gamma. And in the same way, during the negative half cycle also, we are going to get the output voltage is equals to Vs minus V gamma. Since a rectified output voltage occurs during both positive and negative cycles of the input signal, this circuit is called a full wave rectifier. Also notice that the polarity of the output voltage for both cycles is the same. And here is the output voltage waveform. The output voltage is equals to Vs minus V gamma. Here there will be small reduction in the output voltage. Here this is the output voltage. Red line shows the output voltage which is less than the input voltage peak value. And when we go with the full wave rectification with bridge rectifier, the output voltage will be equals to Vs minus 2V gamma. Here if we apply the KVL from the input to the load, that is plus V gamma plus V0 minus plus V gamma and minus Vs is equals to 0. Here V0 is equals to Vs minus 2V gamma. And in the same way, in the negative half cycle also D3 and D4 conducts. So the output voltage is equals to Vs minus 2 V gamma. Now let us go with the numerical problems on full wave rectifier. A full wave center tapped rectifier circuit is shown in figure. Assume that for each diode, the cut-in voltage is 0.6 volts and the diode forward resistance is 15 ohms. The load resistance R is equals to 95 ohms. Determine peak output voltage and V0 across the load R. And sketch the output voltage and label its peak value. Here, in order to get the peak value, Vs peak is equals to 125 by 25, which is equals to 5 volts. And V gamma plus ID into 15 plus ID into 95 minus Vs peak is equals to 0. Here ID is equals to 5 minus 0.6. 5 minus 0.6 by 110. 5 minus 0.6 by 110. Because Vs peak is 5 minus here, which we are taking 0.6, is the forward voltage. Forward voltage is given as 0.6 volts divided by 110, which is equals to 0.04 amperes, where V0 is equals to 95 into 0.04, which is 3.8 volts. This is the way we are going to get the output voltage in the full wave rectifier with the given conditions. Calculate the transformer turns ratio and the peak inverse voltages for each type of the full wave rectifier. In this, we need to calculate the turns ratio and peak inverse voltages for both center tapped and bridge type full wave rectifier. Assume the input voltage of the transformer is 220 volts, 50 Hz from AC main line source. The desired output voltage is 9 volts. Also assume diode's cut-in voltage is 0.6 volts. Here, first let us consider it is of center tap transformer. Vp by Vs is equals to N1 by N2. The peak output voltage is equals to 9 volts. Hence, the output voltage is equals to 9 minus 0.6, that is equals to 8.4, where Vs is equals to whatever the source voltage is equals to 9 plus 0.6, that will become 9.6 volts. And here the peak value is equals to Vrms into root 2, where Vrms is equals to 9.6 by root 2, which is equals to 6.79 volts. The turns ratio of the primary to each secondary winding is N1 by N2, that is equals to 220 by 6.79, which is equals to 32.4 is the turns ratio of primary to secondary winding. Now, peak inverse of each diode, peak inverse voltage of each diode is 2 Vs peak minus V gamma. Here, 2 into 9.6 minus 0.6, that is equals to 19.6 minus 19 19.2, this one. 19.2 minus 0.6, which is equals to 18.6 volts. When we go with the same problem with the bridge rectifier, here we are going to take Vs value as V0 is equals to Vs minus 2V gamma. Here Vs is equals to 10.2 volts. 9 plus 2 into 0.6, which is equals to 10.2 volts. And peak value is equals to Vrms into root 2, where Vrms is equals to 10.2 by root 2, which is equals to 7.21 volts. The turns ratio of primary to each secondary winding is N1 by N2, which is equals to 220 by 7.21, which is equals to 30.51. Here, the peak inverse voltage of each diode is Vs peak minus V gamma. Here only one diode will be conducting. So here, the peak inverse voltage will be minus V gamma, that is 10.2 minus 0.6, which is equals to 9.6 volts. In this session, we have discussed what is full wave rectifier and how we are going to get the output voltages, and rectifiers with filters, and some numerical problems on full wave rectifier. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.